In our previous class, we had discussed about voltage divider bias and different bias techniques. So, different bias techniques we had discussed. In that, we had discussed only about voltage divider bias because we will be having only a topic, and that is called as universal bias. Why it is called as universal bias? Voltage divider bias. Universal bias. This voltage divider bias is called as what? Universal bias. Why it is called as so? It is universal in the sense in major of the circuits we will be using this bias technique only. Okay, so this voltage divider bias means the advantage of having only one voltage supply, and we will have voltage divider resistors to have that voltage drop across the circuit, where we want what amount of voltage, we will decide that by the resistances connected in the circuit. So resistors, voltage divider resistors are very important to be chosen to make certain voltage drop, and that voltage drop across certain resistance or certain resistor will bias the input and output terminals or input and output circuits of your transistor amplifier. Okay. Yes. Now we will see the circuit what we have discussed in the last class, because now we have to go with the equations on the basis of that particular voltage divider circuit. We have taken a silicon transistor which is n-pn type, isn't it? So we have the terminals, collector, base and emitter. Now we will see for the circuit components. Now we have the circuit drawn, and herein we have different resistors. These two are R1 and R2 are voltage divider resistors. This is your collector current limiting resistor RC, and this is your RE, which is your emitter terminal resistor, and this is very important to have the collector current to be stable. And now here we have two bias voltages, that is VBE, so that is the voltage across your base to emitter terminal, and VCE, that is your voltage across your collector to emitter terminal. So this voltage will be dropped, and we have VC, that will be the voltage drop across your RC, and we have VE, which will be the voltage drop across your resistance RE. Okay, so now after all this, so we will go for the equations now. What have we learned about this R1 and R2 resistors? How this voltage divider resist bias will help us with only one power supply, because like here we have VCC, so this voltage will be coming to both your output circuit and the input circuit, and single voltage supply will make the work of your biasing. So then here what we have here is, so VCC will come like this, and certain voltage will be dropped across R1, and rest of the voltage will come out here, and rest of the voltage will be dropped across your R2, isn't it? So now the voltage dropped across your R2, that is called as V2. It is very much important because this voltage drop will be biasing your base to emitter terminal, or what is that? Input terminal. And here what happens to the output terminal is, so VCC voltage will be coming like this over here. So here RC will make a voltage drop of VC, so that is voltage drop across your collector terminal resistor, and remaining voltage will be coming here across your collector to emitter terminal. So that we will have certain voltage drop. That is that, what is that voltage? It is the voltage across your collector to emitter terminal. And at last we have RE. RE will have the voltage drop of VE. Okay, so likewise we have all these things. And coming to voltage divider rule. What is that voltage divider rule? So voltage divider rule, we have discussed this one in our previous year. So about voltage divider rule, how the voltage will be divided across the resistances in a circuit. Okay, so voltage divider rule. So if we apply voltage divider rule to your input terminal, what will be the voltage drop across your V2? Because this is of very much interest for us. So the voltage drop across your V2 will decide what this voltage drop across your VDE, or V2 is the important voltage which will bias your base to emitter terminal. That is why we have to calculate V2. How we can calculate V2 is by applying voltage divider rule at this input terminal. So what it is going to be is, so how I can write this as, this is your supply voltage and this is one of the resistance. This is another resistance. How I can find the resistance across or the voltage drop across this resistance? How we can do that? So we have discussed this. We have studied this in previous classes, isn't it? What is that? How we can do that? It is V2 can be written as VCC into R2 divided by R1 plus R2. Isn't it? Yes or no? So we have studied this, isn't it? So the voltage drop across, this is your supply voltage. So we have two resistances which are connected. Okay. So now voltage drop across this resistance can be found by the formula. What is that? It is the supply voltage multiplied with the resistance, isn't it? Divided by this resistance plus this resistance, isn't it? So this is how we can go for the voltage divider rule, and I can find V2. What is that? The voltage drop across your resistance R2 can be found by using this formula. V2 is equal to VCC into R2 by R1 plus R2. So we have to remember this very finely. So supply voltage into the resistance across what you are going to find the voltage drop into or VCC into R2 divided by the sum of two resistances. So this is how we can find the voltage drop across your R2 resistance, that is V2. by applying the voltage divider rule, isn't it? Okay, so this is how we can go for the formula for finding out the voltage drop across your R2, and once we have found this V2, so we can go for the input circuit to find the voltages. So now if I apply KVL to this loop, what I will get is applying KVL to base circuit. If I apply KVL to base circuit, what it will be? It will be the applied voltage plus VBE plus VE, isn't it? Fine or not? Yes or no? So, and I write the currents to where this is your IE, this is your IB, and this is IC, isn't it? IC is the collector current, isn't it? Yes. So what I can write here is, so V2 is equal to VBE plus VE, isn't it? So if I apply Kirchhoff's voltage law at this loop, okay, so what I will get is that this is V2, the voltage drop across your R2 will be equal to this voltage drop across your base to emitter terminal plus the voltage drop across your emitter resistance, isn't it or not? Okay, so this is how I can write this as what V2 is equal to VBE plus VE, and how I can write VE as that is equal to V2 is equal to VBE plus IE RE, I can write it as, isn't it or not? Fine? Yes. So IE RE will be writing it as, and what we know is, so here I have written it so and so. Fine? Is that okay? Yes. So by this, what I can write it as is, so what we know about our currents, so I can write IE is equal to the collector emitter current, or what I can say it as what? IE. The total current IE is equal to IC plus IB, isn't it or not? Okay. So we know that your emitter current or the current which will be flowing through your transistor, I can write it as what? IE, that is equal to IC plus IB, isn't it? IE can be written as IC plus IB, isn't it or not? Okay, so as we know that IB will be very small, isn't it? IB will be very small. That is why what I can write it as is IE will be approximately equal to IC, isn't it? So IB will be very small. So then I can write it as IE will be approximately equal to what? IC, isn't it? Okay, so if I use this thing over here, what I can write is V2 is equal to VBE plus IC RE. Okay, after all that, what I can write for IC now? So IC can be written as IC is equal to, how I can reorganize things and how I can write that? V2 minus VBE divided by RE. Fine? Okay, so once I know the things V2, so here what I can do is I can calculate the current which will be flowing through the transistor IC with this formula V2 minus VBE divided by RE. So this is one of the important formula what I can what we have to remember. Okay, so if I know the resistances R1, R2 and VCC, I can find the voltage drop across your R2 by voltage divider rule. Okay, with this formula, once I get V2, so I can go for this formula to calculate what? To calculate the collector current, okay, or the current which will be flowing through the device, or you can say the circuit or the transistor circuit or amplifier, we can say it as. So once we are making it to work as an amplifier. Okay, so now I have biased the circuit using voltage divider rule, and these are the formulas to find out the different or the expected current what we will be getting through your transistor, and what will be the current which will be flowing through your transistor, that is IC. So IC is equal to V2 minus VB divided by RE. So this is very important formula, and this is how, if I know the resistance values and the supply voltage, I can calculate V2, and after V2 I can calculate IC, the current which will be flowing through your device. So by these two things, formulas, we can go for your calculations very finely. Okay, so this is how we will be going for the voltage divider rule and KVL application to find out the voltage drop across your V2 and your collector current IC. Okay, so likewise, if I apply your KVL at the output terminal, so I can write this KVL, applying KVL to collector circuit, or I can say it as for output circuit. So collector circuit, if I apply KVL, what it will be? It will be VCC is equal to VC plus VCE plus VE, isn't it? Isn't it or not? Fine? Is that okay? So this voltage will be the voltage, this voltage will be equal to the voltage drop across RC, VCE and RE, isn't it or not? Okay, so it is the sum of VC plus VC plus VE. Okay, so this is how I can apply KVL to your output circuit, and what I can do here is different things. What we can go for is, so if I go for VCC is equal to, what I can write VC as it is IC RC, isn't it? Okay, so VC is equal to ICRC plus VCE plus IERE, isn't it? Okay, fine or not? Okay, so this is how I can write it as. So now again we know that what is IE, what is IE? IE is approximately equal to IC, so I will substitute for IE here. So it will be VCC is equal to what? It is ICRC plus VCE plus ICRE. Okay, so if I rearrange the things, what it will be? It will be VCC is equal to, how I can take IC common, it is VCE plus IC common taken, it is RC plus RE. Okay, after all this, I can write the equation for IC as IC is equal to, so rearranging the things, so I will write the equation for IC as IC is equal to what? It is VCE minus, VCC minus VCE divided by RC plus RE. So this is where we can go for another equation for your collector current. So IC can be written as what? The supply voltage minus the voltage across your collector to emitter divided by this resistance plus this resistance. So this is your collector current equation at the output circuit by applying your Kirchhoff's voltage law. Okay, so this is wherein we can go for the two of the equations for your IC and IC at your output terminal and IC by looking at your input terminal. We can go for these three equations, and these equations are very important. You will be asked to calculate the collector current and voltage drop across your R2, and they will be asking you about the VBE and what will be the value of your IB and what will be your value of IC. All these things they will be giving to find out for 5 marks. They will be giving you 5 of the things to be calculated, and these formulas are very important, and voltage divider bias is very important on the point of examination. So this is very important bias technique, and this is what is called universal bias. Okay, single bias voltage will be used to bias the base and the collector terminals. Okay, so yeah, this is all about these things. And if I see some things over here, so how we can go for this? So see here, so we have VCC and we have RC and RE, and these two voltage divider resistors R1 and R2. So if I see, so what I can make out is, so if we have certain variation, certain like listen, so what will be the voltage drop across your collector to emitter terminal is, so voltage drop across your collector to emitter terminal can be written as what? So it is VCE is equal to, so the voltage applied VCC minus, what I can write as what it is? It is VCC minus VC plus VE. I can write it as VCE. Okay, so this is where we can go for the VCE. So VCE can be written as what? It is VCC minus VC plus VE. The same formula what we have written. So VCE can be written as what? So VCC minus VC plus VE I can write it as. Okay, so now what is the beta? What we have calculated, like what we have discussed in our previous video. So what is that? It is your beta is what? It is the collector, or what we can say it as what? Current gain. Okay, so what is current gain? Current gain beta in your common emitter configuration can be written as what? Beta. So common emitter configurations, your transistor common emitter configuration, the beta can be found out as what? Beta is equal to what? It is beta is equal to output current. What is output current here? It is IC, and divided by input current. What is input current? It is your IB, isn't it? So beta can be written as what? IC divided by IB. So how I can write for your IC then? IC can be written as what? Beta into IB. So your collector current is related to base current. Okay, so beta can be written as what? It is not beta, yes, IC, or collector current can be written as what? IC is equal to beta into IB. Okay, so beta into IB. So I'll write it over here. IC is equal to beta into IB. So input current will decide the output current, and beta is the current gain, isn't it? Current gain is your common emitter configuration, and beta will decide how much times your output current will be than your input current. Okay, so beta value will range from 100, 200, so many times gain it will be talking. Okay, so beta value is very important in terms of finding out the different things. So if you know IB, you can calculate IC also. Okay, without going for all these formulas. Okay, so IB won't be given usually. So sometimes in some of the problems they will be giving about IB. So if they don't give, you can go for all these things to calculate your IC by doing your V2 voltage drop across your input resistance, or the what we can say base to emitter circuit resistance. So this resistance is very important, and this resistance voltage drop will bias the base to emitter terminal, and this is where we are having the voltage divider bias, and these two resistance selection is very important in terms of the voltage drop required. Okay, so this is all about the calculation, all the formulas which will make out the total voltage divider bias, and in next class we will solve some of the problems on the voltage divider bias circuit. Okay, thank you.